Hello, hello. This is gonna be the Chem 8B quiz 3 review session. How are you guys feeling about the quiz so far? Are you guys feeling ready? There's a lot of stuff for this upcoming quiz, like Friedel-Crafts alkylation, acylation, the ortho-para director, meta director, your EDG, WG, chemistry, EM information, ENM information. Like there's a lot for sure. Um, so what we could do is we could go over the vocabulary section questions here, or we could like walk over the practice quizzes that Lievens posted on her Canvas, like practice quiz 3 and 4 that she posted. Or I could go over the reactions mechanisms for you guys before we go over that. Do you guys want to start off with anything before we get started? Right. Any topics or any questions you guys want me to go over? Electrophilic aromatic substitution. Okay, let's do that. So EAS, aka electro. Oh my god, we'll be back. Oh my. Oh shoot, I was muted the whole time. Okay. Um, so electrophilic aromatic substitution, aka EAS mechanism, is going to have a benzene acting as a nucleophile, right? And there's going to be 3 general steps for the mechanism. The first step is going to be form the electrophile, and the electrophile here is going to be different for different reactions, right? There's halogenation, there's nitration, there's sulfonation, and then there's the Friedel-Crafts one, Friedel-Crafts alkylation, Friedel-Crafts acylation. For this quiz, you guys need to worry about the alkylation and acylation one. The second one is going to be addition, and then the third one is going to be elimination, right? And here's the general mechanism here. So let's say we have our electrophile present already, and we have our benzene here present. Let's say this is an empty benzene ring with no groups attached to it, no EDG, no EWG attached to it. If that's the case, then if I put in an electrophile in there, any carbon of the benzene could be my nucleophile and attack the electrophile to form the new bond, right? So I'm going to choose this carbon here to attack this electrophile, making a new bond between that starred carbon that I just starred and the electrophile right there, right? So if I were to highlight this bond here in blue like that, that's this blue bond right there between the starred carbon and the electrophilic carbon right there. Okay, and we see that this carbon here lost a bond, so this carbon here will be positively charged. Okay, so now, would you guys say this benzene ring is aromatic, non-aromatic, or anti-aromatic? Based on if it fulfills the 3 conditions, is it cyclic, fully conjugated, planar, and if it is, does it follow Huckel's rule or not, like 4n electrons or 4n plus 2 electrons? Yes, it is going to be aromatic. right? And aromatic molecules are stable. So this benzene ring right now is aromatic, happy, and stable, right? But when we added the electrophile into this benzene ring, we broke the aromaticity, right? Aromaticity here is broken. Broken, right? So now it's less stable. So to restore the aromaticity, that's when we go in with the third step here, elimination. So we're going to bring in some sort of base to do an E1 mechanism. Deprotonate that carbon, grab that hydrogen. The bond between this carbon and hydrogen right there is going to make a double bond right there. And that's going to give us this restored aromaticity back. So if I highlight this bond in pink right there, that's this pink bond right there. This is still the blue bond from the original benzene right there. And we restored aromaticity. Restored aromaticity. Okay, so that's going to be the general mechanism for all of the EAS reactions that you need to know, which is halogenation, nitration, sulfonation, and the Friedel-Crafts reactions. Know those two for this upcoming quiz. Friedel-Crafts alkylation and Friedel-Crafts acylation. So for this upcoming quiz, let's go over Friedel-Crafts alkylation first. I'm gonna give you guys a practice problem to work with, and then I'm gonna give you guys a few minutes while I go get some water really quick. Let's say you have that empty benzene ring. We didn't go over EDGs, EWGs yet, orthopara-directors or meta-directors yet. So let's say you have that benzene reacting with this set of reagents here. Okay, predict the product and draw the mechanism just for extra practice. And I'll give you guys 3 to 5 minutes for this, and I'm gonna get some water really quick. Okay, I am back. Have you guys had enough time to draw out the mechanism, predict the products for this one? Yeah. If not, I could go over how to predict the product first just by looking at the reagents and reactant, right? How to do it quickly without doing the mechanism, and then we could go over the mechanism. Does anyone have the products ready? You could send a screenshot here or describe to me what it looks like or show it on the camera if you guys are comfortable with that. Right. Okay, so to predict the product quickly here, this is what I think about when I think about Friedel-Crafts alkylation. I always watch out for carbocation rearrangement. That's the most important part about this mechanism, this reaction, right? That's the one that makes this reaction the hardest EAS reaction, right? So we see here that just imagine this good leaving good leaving. If we have that good leaving good leave, this carbon here will have a positive charge, right? Which can be shifted to this more sub position here, the more stable substituted position by a hydride shift, right? So we know that the intermediate somewhere is going to have a positive charge on that more sub position right here. This carbon right here, which I'm going to dot as a red dot, right? It's not going to be this position because that's the less stable, less substituted carbocation, right? And now, since I dotted that carbon, I'm going to star one of the carbons here of the benzene. It does not matter which carbon of the benzene attacks this electrophile because this benzene has no groups attached to it, right? No EDGs, no EWGs, no directing groups. So if I use that as my starred carbon, I'm going to make a new bond between the star and dot carbon right there. This is the new bond between the nucleophile and the electrophile. Now, I'm going to draw out what is... Wait. Someone said they can't hear me. Can you guys hear me? Just making sure, confirming. Hello, hello, testing. Yes. Okay, okay. Let me fight this first in. Okay. Connecting to a different device. And everyone else can hear me. Okay. So this is going to be the new bond between the star and dot carbon. Now, this is why I dot the carbon here. It helps me keep track of all the groups to this dot carbon. This dot carbon is attached to 2 methyl groups and 1 ethyl group right there. So I'm going to draw that out like this. Ethyl group coming out right there, and 2 methyl groups coming out of the dot carbon right there. And that's how I can predict the Friedel-Crafts alkylation product without getting messed up and adding an extra carbon by accident or losing a carbon by accident. Right? So that's how we could do it quickly if this was predicted product. To save time on the quiz, because Lievens quizzes are like time restrained for sure. Okay. Now, any questions on this before we move on to the mechanism, the actual mechanism on how to convert these set of reagents into this? Why would we not just attach from the carbon where the chlorine was attached to? Yeah, that's a good question. A lot of people, right, would have added, like, let's say, where this chlorine here was attached to. Let's make that the green dot, right? And let's say that you make a new bond between this red starred carbon here to this green dot right here. The leaving group leaves, so it's dissolved into an ion now. Or it is going to leave from this molecule, right? If we attach this red star to that green dot, that green dot is attached to a sec-butyl group. And I'm going to draw that sec-butyl group out like that, right? So some people might have put this as the answer. This is not the answer because of the carbocation, right? Think about the carbocation intermediate here. We want to form the more stable carbocation intermediate, the more substituted one. If you went the green route, the intermediate would have had, like, you could think of it like this in quotation marks. This is actually not like gonna be formed here. A carbocation on this position here, which is less stable than this tertiary position. So if I talk about carbocation stability, a methyl carbocation is the least stable, and then we have a primary carbocation, and then a secondary carbocation, and then a tertiary carbocation. And there is something more stable than the tertiary carbocation, which is secondary allylic, which I don't think you guys went over yet. So I won't go over that. But notice how the more substituted or the more friends the carbocation has, the more stable it's going to be, right? And that's due to hyperconjugation, more hyperconjugation, right? So that's the most confusing part about this Friedel-Crafts alkylation reaction. We gotta watch out for that carbocation rearrangement step, that sneaky step right there, which is gonna give us this major final product right here, right? Where did the second methyl group come from? The second methyl group right here, so let's say if you look at the red dot right here, this red dot has two methyl groups, one here and another one here, right? So that's that one here, another one here. Let me highlight the groups for you to make it more clear. Let's say this is red, that's that red methyl right there. Let's say this is pink, that's that pink methyl right there. Let's say this is blue ethyl, that's that blue ethyl right there. That red dot carbon is still there. This is the new bond between them. If I highlight this bond here in orange, that's that orange bond right there, the new bond right there, right? How does AlCl3 play into our final product? Yes, so AlCl3, that is a metal catalyst. A metal catalyst, which in the mechanism, it gets reformed, right? Because in catalysts, the mechanisms gets reformed. It would not be included in the major product. It would be reformed. You might also see it as a Lewis acid, right? It's a metal catalyst and a Lewis acid. So keep those terms in mind for the vocabulary section for Lievens quiz. Right, it's a metal catalyst. It gets reused, reformed, which we're gonna see that when I go over the mechanism into play, right? Okay. Any other questions on this? For this problem, would we need to worry about the type of directors? No. This problem, we don't have to worry about the type of directors because the benzene here has no substituents attached to it. No activators, no deactivators, no electron donating groups, no electron withdrawing groups. So we don't have any ortho para directors. We don't have any meta directors, right? So if there's no groups, we could attach that into any carbon here, right? Okay. I'm gonna go over the mechanism of this before going over the problems of the Friedel-Crafts alkylation. Right.
Just a question. You think that
Yeah.
the mechanism for this problem will be maybe tested, correct?
Yeah, this
Most likely
and,
to.
and Friedel-Crafts acylation, there's a high chance that this is gonna show up in the mechanism.
Okay.
Friedel-Crafts alkylation, Friedel-Crafts acylation, yes. And imine formation and enamine formation, those mechanisms as well. It's gonna be very, very high likely chance. So one of those four mechanisms, I would bet it's gonna be on the quiz tomorrow.
Okay, perfect.
Yeah. Okay. Okay. Now, let's move on to the mechanism. So earlier, I separated the mechanism into 3 steps. The first step was to form or generate the electrophile. Form the electrophile. Let's bring in my haloalkane or alkyl halide. And we have our metal catalyst, AlCl3. Now, I'm just going to explain things conceptually here so you guys can understand the reasoning behind each arrow, each charge, and each pair of electrons. This aluminum here has 3 bonds. 1, 2, 3. It's missing a bond, missing 2 electrons, right? So that means that it has an empty p orbital right now. But it's one of those weird atoms like boron that's going to be neutral when it's electron deficient, when it has 3 bonds like that, right? But it still has a empty p orbital, which this chlorine here, one of its pairs of electrons, let's say those pairs of electrons, is going to attack that aluminum, right? Give that aluminum 2 pairs of electrons. So when that happens, we're going to get something like this right here. Chlorine, aluminum, and this aluminum is attached to 3 other chlorines, right? And this aluminum now has 4 bonds. 1, 2, 3, 4. Aluminum with 4 bonds, like boron or iron, is going to be negatively charged, like that, right? And this chlorine here with 2 bonds is going to be positively charged. That's because of the formal charge. Like before, it had 3 pairs of electrons, now it has 2 pairs of electrons. To calculate formal charge, look at the periodic table, see how many electrons it wants. And chlorine is on the 7th column of the periodic table, so it wants 7 electrons. But it has 1, 2, 3, 4, 5, 6 electrons to itself. So 7 minus 6 is positive 1. That's why chlorine has a positive 1 charge there. So that's how you could calculate formal charges. Now, think of this whole group right here that I'm going to circle as a good leaving group. Right? But to proceed with the mechanism here, because this is not a secondary or tertiary substrate, right? I'm going to make that into like a red dot right there. Because this is not secondary or tertiary substrate, the good leaving group could just not leave by itself, right? But when it leaves by itself, it's going to form a primary carbocation. And primary carbocations are too unstable to form, so we don't want that, right? So that's the reason why in this particular case, the leaving group does not leave by itself, because of that very unstable carbocation intermediate. So what we're going to do is a concerted hydride shift. I'm going to explicitly draw out a bond between the nearby carbon that is going to be more stable for the carbocation and its hydrogen right there. I'm going to shift that bond and its hydrogen to that carbon right there, kicking out the leaving group at the same time, right? And that is our concerted hydride shift. Concerted hydride shift. Okay, as a result, we are going to get this intermediate here, where this carbon right here, which I'm going to make a bigger red dot right there, lost a bond. So that's why that carbon is now positively charged. It has a carbocation. Now, I'm just going to draw out the bond to the hydrogen to make it more clear, like where that came from. Like let's say we highlighted that bond with the hydrogen right there. That's this yellow bond with the yellow hydrogen right there. Right, that was not here before, right? This had 2 hydrogens before, and it's 2 hydrogens. I'm going to leave it as invisible like that. Okay, and now if this is mechanism, include everything. So the leaving group that left is this negatively charged AlCl4, aluminum Cl4. Okay, so now let's do the second step. That's always the hardest part, the first step, forming the electrophile. This is our electrophile here, that positively charged carbon, right? It's different for each reaction. Now let's do the second step, which is addition. Since this is an empty benzene ring, does not matter which carbon attacks. Let's choose this carbon here as a nucleophile and attack that carbon right there. New bond between the star carbon and dot carbon. That's the new bond that was made between them. This dot carbon here is attached to an ethyl group and 2 methyl groups, right? Ethyl group for that and 2 methyl groups here, 2 methyl groups there. This carbon here lost a bond, so that carbon would have a positive charge, right? Now this is when we move on to the third step, elimination, to restore the aromaticity, right? Because we just broke the aromaticity. To do that, if this was a mechanism problem, you would have to explicitly draw out that hydrogen there, attached to that carbon. And then the base here that is going to grab that hydrogen is the AlCl4 minus that got kicked out earlier in the previous step, right? This angry aluminum with a negative charge here will actually have this chlorine with this bond attack that hydrogen. This bond here between the hydrogen and carbon will move and go onto that carbon right there to give us our final product, that restored aromatic ring with the alkyl group attached to it, like that. And we also see that the AlCl3 lost a chlorine, right? Because we also formed HCl here as a side product. Include that if this is mechanism. This AlCl3 metal catalyst gets reformed. So if I highlight this Cl here, that's this Cl here. If I highlight this hydrogen there, that's this hydrogen right there. Okay, now this is the whole mechanism. Let me know when you guys have any questions before I move on to the problems of Friedel-Crafts alkylation. And this reaction in particular is the hardest one to follow along with the note card, because there's different scenarios for like this reaction. There's the one we just did, the primary hindered substrate, which we do a concerted hydrogen shift. There's a secondary or tertiary substrate, which we do not do a concerted hydrogen shift. We do a regular hydrogen shift when the leaving group leaves first. So this reaction here is the hardest one to follow along with the note card. But any other reaction like nitration, sulfonation, halogenation, physical isolation, it's much more easy to follow along with the note card, because nothing like changes as much and everything else is decoration. Right. What is the difference between a regular and a concerted hydrogen shift? Yeah, so that's a good question. A regular and a concerted hydrogen shift is different because let's say we have, let's go back to Chem 8A. Let's say we have this haloalkane right here, and we have water. We have a secondary substrate, we have a good leaving group, and we have water, which is a poor base, poor nucleophile. But I'm going to say that's a weak base, weak nucleophile as my reagent. What reaction comes to mind when you guys see these reagents? Secondary substrate, good leaving group present, and a weak base, weak nucleophile. Would it be SN2, SN1, and E1, or E2? So E1 and SN1, they will both happen together, right? Where the major and minor product, like the major product would be SN1, and the minor product would be the E1, unless you add heat to it. So the first step of the mechanism, kick out the leaving group. And we were able to do so because we are able to form the stable carbocation to exist. This secondary carbocation right here, right? But whenever we form a carbocation intermediate, right, you gotta stop and you gotta look out for any rearrangements. Either a hydride shift or a methyl shift. Right? In this case, to do that, this is our secondary carbocation here. Look to the adjacent carbons nearby. See if you can move that carbocation to a more stable position or not. We see that there is a more stable position on the left side because it's more substituted, right? But do not draw that arrow like that. Like, do not draw the arrow from the positive charge going towards that carbon right there. We want the positive charge on that carbon, but it doesn't move like that in mechanism, right? Because the arrows represent the movement of electrons. There's no electrons here, so there's nothing to move there. So to do that, I'm going to explicitly draw out the invisible hydrogen with its invisible bond to do a regular hydride shift. I'm going to move that bond with its hydrogen over to that carbocation. And I'm just going to draw it out here, but we could leave it as invisible in the mechanism. But that hydrogen is that hydrogen right there. Before, this carbon here had 4 bonds, right? 1, 2, 3, 4. But because this hydrogen moved with its bond, this carbon now only has 3 bonds. It lost the bond. So its formal charge is now positive. So that's how the positive charge moves, right? We fill in a void to just create another void right there, but a more stable void, a more substituted void, like that. So that's a regular hydride shift right there. And then we could continue with the reaction, but you're not tested on this reaction, so I wouldn't worry about that. Now, for a concerted hydride shift, it would be something like this. Let's say you have the same set of reagents, so it's going to be SN1, E1 as well. But in this case right here, we have a primary hindered substrate, meaning that this carbon here is primary, and it's hindered because adjacent to it, there's at least 2 branches, right? So this good leaving group here cannot leave by itself first, because when it leaves by itself, I'm going to do it in pink, which is the incorrect way. We're going to form this extremely unstable carbocation intermediate, too unstable to exist, right? So we don't want that primary unhindered carbocation. But we do see that next to it is a more stable position. So let's draw out that invisible hydrogen with this invisible bond again to do a concerted hydride shift. And I'm going to do this in blue, which is the correct route. Move that hydrogen over and kick out the leaving group at the same time. That's the concerted, meaning simultaneous, hydride shift, right? The leaving group and the hydrogen shifts at the same time, concerted with each other, right? Simultaneously. Concerted hydride shift. Right? In the previous example that we did, the hydride shift happened when we already had the carbocation, right? The leaving group left first as the first step. Leaving group leaves first, and then we do the regular hydride shift. But for the concerted hydride shift, we do the hydride shift and the leaving group at the same time, simultaneously, to give us this tertiary carbocation right there. And that is the difference between a regular hydride shift and concerted hydride shift. Any questions for that? Okay, so now let us go over the problems with Friedel-Crafts alkylation. Right? Problems. There's two big ones I want you guys to know. Number one is the one that we just went over. Carbocation rearrangement. Right? Because let's say in synthesis, you want to convert this benzene into this benzene with this alkyl substituent here, like that. And let's say that you tried adding this substituent to do so. That would not work, right? Because if you actually did that, this would be your product instead. Right? Where if I red dot that carbon, that's this red dot carbon right here. If I green dot this carbon, that's this green dot carbon right there. And the reason why is because of the carbocation rearrangement. The other big problem for Friedel-Crafts alkylation, and this is going to be more likely for like vocab section question, is going to be over-alkylation. And this is going to segue into like the EDG, EWG, orthopara-director, meta-director. So let's say we have CH3 Br FeBr3. We're going to add that methyl group to that benzene right there. Yes, I can go over organometallics and reversible addition after I go over this reaction. Yes, let's go over that. Okay, so we added an R group here, an alkyl group, right? And that R group is an EDG by induction. It would naturally just donate electrons into the system, the benzene system, naturally, right? There's no pairs of electrons on that carbon right there, so we cannot donate electrons by resonance, right? And do you guys remember if an EDG is an orthopara-director or meta-director? What would an EDG be? Orthopara-directing or meta-directing? Orthopara-directing, right? So before we go over that, let's say we have a substituent right here. The ortho position is one carbon away from the substituent. So that's the carbons in blue. The meta position is 2 carbons away from the substituent. Right, so these are position terms. The para carbon is going to be across, parallel to the substituent, like that, right? So a way to remember this is that if you think about the meta position, let's say there's something meta to it. If you trace along the R group to the other R group, they kind of make an M shape, right? M letter, M for meta. Para, the way that I think about it is that the groups are parallel to each other, anti to each other. ortho is like orthogonal to each other, adjacent to each other, next to each other, like that. So just know those position terms. But be careful here, right? It's not always going to be in those positions because our R group here could be different. Let's say our R group is down there. Now our ortho positions would be here. Our meta positions would be here. And then our one para carbon would be that carbon right there. Okay? So if this is our substituent that we're worried about, I'm going to star my ortho and para positions, right? I'm starring these carbons because those are my nucleophilic carbons. We said they're ortho para directors, right? So these positions I start here, these are the ortho carbons. This is the para carbon, right? So we're going to have multiple reactions here because we just activated the ring with this EDG. When we activated the benzene ring, it's gonna do this reaction one more time. It's gonna do it like 2-3 more times, right? So let's give out the para product. This is the para product. We could also have the ortho product, which is like that. So that's another problem, over alkylation. We have multiple reactions once we activate the ring to have multiple products which are undesired, unwanted. Yeah, I could explain carbocation rearrangement again briefly. So carbocation stability. Methyl, least substituted. Primary, secondary, tertiary. The more substituted the carbocation, the more stable it is. In all mechanisms, whenever you form some sort of carbocation, you stop and you look out for any carbocation rearrangement, meaning that if you see there's a more stable position nearby, move that. Well, we don't like move the carbocation directly, but we want to move it there by doing a hydride shift. Move the bond with the hydrogen over there to that carbon, which is going to give us this tertiary carbocation right there. So that's a regular one, right? But let's say we have a good leaving group right there, and at the primary position, that cannot form a carbocation to begin with because that's too unstable to exist, the primary carbocation. But there is a more stable position nearby to host the carbocation. So we're going to do a concerted hydride shift. The hydrogen moves over to that carbon, kicking out the leaving group at the same time, simultaneously, which gives us this tertiary carbocation right there, right? So this top part is the regular hydride shift. This bottom part is the concerted hydride shift. Yep. EDG stands for electron donating group. Yeah, electron donating group, which is also known as an activator, right? And all activators, all EDGs will be orthopara directors, right? But when we get into EWGs, deactivators, most EWGs, most deactivators are what? Like what directing group are they? They gotta be, there's only one position left, meta directing, right? And if they are meta directing, right, they're gonna direct the group electrophile meta to the substituent, meta to the EWG. But yep, that's the exception, halogens. Halogens are EWGs, but they are not meta directors. They are orthopara directors. And I can explain that conceptually if you guys want to later. Right. Okay, so those are the two problems for Friedrich-Gauss alkylation. Now, let's go over carbonyls, what someone wants to go over. Irreversible nucleophilic acyl substitution addition and reversible nucleophilic acyl addition with organometallic reducing agent and the reversible ones. So carbonyls. When you see carbonyl, I also think of it as an acyl group, which is a carbon double bond oxygen. That is a carbonyl group. This is a big umbrella term because there are many carbonyl functional groups. Can you guys name me multiple functional groups that has a carbonyl? There's gonna be like, I want you guys to name like 1, 2, 3, 4, 5, 6, 7. 7 at least. Ester, okay, that's one, which is gonna look like this. Right? Aldehyde, ketone amine, yes. So I'm gonna give it in this order actually. So ketone, aldehyde, carboxylic acid, amide, yes. Now there's two more new ones, relatively new ones that you guys have seen not as much as these ones. And there's different types of amides, right? There could be this type of amide, there could be this type of amide, or there could be this type of amide. Okay. Carboxylic acid. Yep. Now there's two more that you guys have barely seen. You guys seen one of them? One of the ones in Friedel-Crafts, let's say acylation. Yeah. I can write the name for these next to them later, after we finish the list here. Acyl halide. Yes, that is the reagent for Friedel-Crafts acylation. Okay, so that's going to be that X right there, where X can be chlorine or bromine, halogen. Yep, formaldehyde is going to be part of an aldehyde. So I'm actually going to draw that out just because Lievens might put that in the vocab section. So that's part of an aldehyde right there. But formaldehyde has 2 hydrogens instead of 1 hydrogen, like that. Okay, now there's one more, which is a weird one, which is anhydride. All right, let me make more space here. Okay. Like that. Yeah, let me label these right now. Ketone, aldehyde, formaldehyde, acyl halide, right? Acyl meaning carbonyl, the carbon double bond oxygen. Halide meaning halogen, chlorine or bromine. Acyl halide, anhydride, carboxylic acid, right? A lot of people think that this is alcohol, where there is an alcohol present, an OH, but it's next to an acyl group, next to a carbonyl. So when you say an alcohol right next to an acyl group or carbonyl, don't call that an alcohol. Call that a carboxylic acid, right? Because you have to keep that carbonyl into account as well. This is an ester. This right here are amides. Okay, so I'm going to make a separation here between that and this right here, right? The ketone and aldehyde and the rest. These ones here are carbonyls with no leaving group attached to it, no good leaving group attached to it, no good leaving group. Whereas all of these carbonyl functional groups here have a good leaving group. And keep this in mind. This is going to be very important for the next upcoming quiz, or I don't know when, but for 8B for sure. Have good leaving groups. And I'm going to circle out the leaving groups right here. Halogen is a good leaving group, like chlorine or bromine. This carboxylate is going to be a good leaving group. This OH will eventually become a good leaving group in the mechanism. OR, good leaving group. And the nitrogen containing group is a good leaving group. So notice how all of these groups here have an electronegative atom, right? That can handle the negative charge when it leaves. So that's why those are good leaving groups. Whereas if we think about these R prime and hydrogens right there, those are non-electronegative atoms, right? They are terrible bad leaving groups. They don't want to have that negative charge at all. Terrible leaving groups. So that may be a conceptual thing, because she did go over that in her lecture notes. Okay. So now, what is the partial charge of this carbonyl carbon here? Partial positive or partial negative? Think about the difference in electronegativity between this oxygen atom and this carbon atom. Which atom is more electronegative, meaning that that atom is the partial positive, partial negative carb atom? Yep, oxygen is more electronegative than carbon. So it's going to withdraw electrons from carbon naturally because it has a stronger pull on the electrons, right? And as oxygen here is gaining more electrons, it's gaining more negative charge, right? Because electrons are negatively charged. As this carbon here is losing electrons, it's losing negative charge, becoming partial positive charge. Now, which one of these here would be our electrophile? Which atom? Oxygen or carbon is our electrophile? Which one? Carbon, yes, because carbon is positively charged and oxygen is negatively charged, so we could call that the nucleophile or base. Right? So that's the most important part for this upcoming quiz. Know that that carbon right there is the electrophile. It could be attacked by some nucleophile, right? And there's going to be two different types of nucleophiles for this reaction. And let's call that reaction nucleophilic azo addition. It's just a fancy name, and I'll show you what that means. Nucleophilic azo addition. Right, but before I go explain that name, let's just explain this right here. Let's say we have some sort of nucleophile present. This could be any random nucleophile depending on what the reaction is. And we have a electrophilic carbon right there. When we attack that electrophilic carbon with the nucleophile right there, we're trying to make a new bond between that carbon and nucleophile right there. So let's say that happens. Let's say we make a new bond right there. There's a problem here. We just broke the octet rule, right? If we don't do anything else, if we don't draw any other arrow, this carbon would now have 1, 2, 3, 4, 5 bonds. That's not good. That breaks the octet rule. To conserve the octet rule, to maintain the 4 bonds, when this nucleophile makes a new bond with that carbon right there, we have to push one of the bonds of the double bond here onto the oxygen, right? There's 2 electrons in one of these bonds here. Those 2 electrons are going to go onto the oxygen right there, right? Where this oxygen originally had 2 pairs of electrons, but when we give it an extra pair of electrons, it's going to have 3 pairs of electrons. So when I give you the mechanism here, it's going to look like this. That oxygen now has 3 pairs of electrons, and this is the new bond between that red dot carbon right there and this nucleophile right here, right? This is the new bond between them. And you can think of it like this. Let's say that that nucleophile used that pair of electrons, which I'm going to highlight in yellow, like that, right? This yellow pair of electrons is that bond right there with 2 electrons. And if I highlight this bond here in blue, that bond's 2 electrons are these, let's say, 2 electrons there as an extra pair of electrons. So that's like how we converted this interaction between this nucleophile and carbonyl electrophile into this intermediate here. Now there's something missing here. There is something missing here. Can you guys tell me what is missing here? This is especially important for a mechanism problem. Like, what am I missing in this intermediate? Formal charge, yes. On oxygen, what formal charge should oxygen have as a result of this interaction? -1, yes. Because it gained a pair of electrons, and oxygen wants 6 electrons to itself, but right now we see that it has 1, 2, 3, 4, 5, 6, 7 electrons to itself. Wait, this is how we do it when we calculate formal charge. It technically has 8 electrons. It does, right? 2, 4, 6, 8 electrons. But this bond here has 2 electrons, 1 for the oxygen, 1 for the carbon. So oxygen here has 1, 2, 3, 4, 5, 6, 7 electrons to itself. 6 minus 7, -1 charge. That's how we calculate formal charge. Right. Okay. Now, once we have this, then we could just bring in some sort of acid, right? H plus source. It could be HCl, H2SO4, PTSOH, any proton source to protonate and neutralize that O minus right there and give us OH, like that, right? This O minus here is going to use one of its pairs of electrons to make a bond with this hydrogen right here, that proton source, right? And I'm making it vague here because it's going to depend on what she gives you on the arrow. If she gives you HCl, then it would be attack that hydrogen, kick out the Cl. If she gives you H2SO4, it's going to be attack that hydrogen, kick out the HSO4 minus, right? Which gives us this neutral alcohol now. And that's nucleophilic azo addition. This is the azo group, right? We added the nucleophile, right here, the nucleophile, onto the carbonyl, right? Addition is the adding part. Added the nucleophile onto the azo. So that's what the name of the mechanism means. Adding a nucleophile to the acyl or carbonyl. Okay. And there's two types of nucleophilic acyl additions that I want you guys to know. There's an irreversible nucleophilic, and I'm going to abbreviate that as NU minus, acyl addition, and irreversible one. But let's go over the irreversible one first. There's going to be, they're going to use irreversible nucleophiles or strong bases, right? And Lievens, she wants you guys to know the pKa for things. So the pKa for these sets of reagents here would be greater than or equal to 25. And there's three that she gave you. There's the one with an R minus, there's the one with a H minus, and there's the one with the alkyne no anion right there, right? But these two are the most important one. Know these two for sure, because the R minus here is going to be your organometallics reagents. The H minus here are going to be your reducing agents. Right? So on the arrow, when you see one of these reagents here, let's say organometallic, there's two types. There's a Grignard reagent, R MgBr, and there's organolithium. They do the same thing though. They have the same chemistry, it's just different reagents, right? RLi. Where the carbon directly attached to the Mg or Li is going to be negatively charged, partial negative charge, the nucleophile. Two types of reducing agents that you need to know: LiAlH4, lithium aluminum hydride, and NaBH4, sodium borohydride. When you see these reagents here, a big sign of a reducing agent is there's a lot of hydrogens here in this reducing agent. There's H4. Think of a hydride ion, a hydrogen with a negative charge that's very nucleophilic, very strong. That's a hydride ion, right? That is a reducing agent. Okay, so these are the irreversible nucleophiles that you need to know, especially the organometallic ones and reducing agent ones. Now, let's go move on to the nucleophilic acyl addition irreversibly. Let's add a basic carbonyl in like that, and let's do organometallic phase, right? I'm going to show you guys how to predict the product quickly before doing the mechanism, and then I'm going to go over the mechanism afterwards. So there's going to be two steps here. First step is going to be something like this. Second step, acid workup, right? Organometallic will always be followed up with an acid workup step if you reactivate with the carbonyl. In this case, we are, because that's the second we're on right now. Okay. So to predict the product quickly here, without looking at the mechanism and save time on the quiz, this is what you do. We know this is a Grignard reagent because we see MgBr. The carbon directly attached to the MgBr, I'm going to star that carbon right there, right? Because I know that that is my nucleophile, but I'm going to explain that in the mechanism. So not talking about any mechanisms at all, just like, you know, do pattern recognition. This is what I do. Star the very first atom attached to the Mg. Dot the carbonyl carbon, the carbon that's double bonded to the oxygen, right? And I know MgBr dissolves away. It just disappears. It goes bye-bye, right? So when I predict the product here, that's this dot carbon right here. This double bond oxygen here becomes a single bond OH, alcohol. This is the new bond here between the star and dot, right? That's new bond right there, new, between the star and dot atom. Then we just attach whatever is attached to the star right here. This star is attached to a sec-butyl. So let's draw the sec-butyl out like this. Carbon out, methyl, ethyl, like that. Okay, so that's how you can predict the product quickly without doing the whole mechanism. If that didn't make sense, then maybe going over the mechanism, like step-by-step arrow would help you visualize how it got here, right? But if you guys don't have time to do the mechanism, this is how I would do it, like the tricks I would do, the things I would do to save time on the quiz. Any questions on this trick before I move on to the mechanism? Yeah, so the mechanism for this is very short, so not likely, right? It's not as involved as the Friedel-Crafts alkylation, acylation, imine formation, enamine formation. Those ones will probably be more likely because it has more steps, more charges to grade on. This one here is like very short, like 2-step mechanism, so not likely. I wouldn't bet on this mechanism on the quiz, but still include it in the quiz just in case. You know, yeah. It's 8 a.m. I know, first thing in the morning for you guys. Oh my gosh, have you guys made your note card yet, or are you still guys working on it? Are you still working on your note card? There's still space. Okay, you haven't made it yet. Okay, yeah, there's still time. There's still time. It's okay. Enamine, yeah, we'll go over enamine after this, which is a good segue because right now we're going over irreversible nucleophilic acyl substitution addition, and then after that we'll go over the reversible part, reversible nucleophilic acyl addition. Yeah. That's good. 10 hours. Okay. And I heard it's like very far away to like Mandavi Center, so you guys gotta like walk if you guys bus. So that's unfortunate. This is organometallic. Organometallic. But in this one specifically, it's a Grignard reagent because we say MGBR, right? When you say MGBR, think of Grignard reagent. Grignard reagent. Right? Reacting with a carbonyl, carbon double bond oxygen. And this is a type of irreversible nucleophilic acyl addition. So the name of the mechanism, this type is an irreversible nucleophilic acyl addition. That's the mechanism name. But the reaction is organometallic plus carbonyl. Lap desks, oh my gosh. You guys gonna do a 20-minute quiz in that center. Well, question 3 from practice question 4. Yeah, hemiacetals would be next quiz, not this quiz. So don't worry about that question. Okay, let's talk about the mechanism now. I'm gonna draw out the Grignard reagent, organometallic reagent like this. Right? We know that for all Grignard reagents, the carbon attached to the magnesium is partial negatively charged, right? Making that the nucleophile. Every other carbon here is not the nucleophile. It's the carbon directly attached to magnesium. And we said earlier that this carbonyl carbon here is partial positive charge because the electronegative oxygen here is pulling on its electrons, right? So here's the mechanism. Have that star carbon attack the dot carbon. But there's a problem there, right? What is the problem and how can we fix it? Like, what happens when we make a new bond between the star and dot carbon without doing anything else, without drawing another arrow? Right, like let's say we just made a new bond right there without doing anything else. Carbon will have 5 bonds, right? One, what that we just made, 2, 3, 4, 5. To conserve the octet rule, we gotta push one of the bonds with the double bond onto the oxygen and get this tetrahedral intermediate here, right? Where this is the dot carbon, this is the star carbon, this is the new bond between the star and dot carbon. MGBR dissolves into ions. Do not include that, it just leaves, right? The star is attached to sec-butyl, so let's draw that sec-butyl out like that. Okay, what am I missing here in this intermediate? How come the star bond is not attached to the most stable carbocation? Yeah, so you're thinking of Friedel-Crafts alkylation, right? Where there is a more stable, more substituted position here, but that is for Friedel-Crafts alkylation, right? That's the mechanism for Friedel-Crafts alkylation. This reaction we're doing right now is Grignard reagent reaction, right? Friedel-Crafts alkylation, this whole alkyl group here acts as an electrophile, positive charge, right? But for Grignard reagents, this whole thing acts as a nucleophile. So this is a different reaction, right? This is not gonna form a carbocation here at all, right? There's no positive charge at this molecule at all. Okay. What am I missing here in this intermediate for the mechanism? Because you will get points off if you like forget about this part as well. And I want you guys to like not lose this point. Right. So this is the common mistake that students forget about too. When they push the double bond to oxygen, they forget to add this one small detail in the mechanism. Adding a negative charge to the oxygen, yes. So any form of charge at all, keep track of them, right? It could be negative charge, positive charge, right? In this case, we're adding a negative charge on the oxygen like that. That's the end of the first step. We're done. Now, we bring in the second step, acid workup, H3O+. I'm going to draw it out like this. Right? That oxygen there with 3 bonds and 1 pair of electrons is positively charged is an acid. So this O- here is going to grab that hydrogen. The bond right here between the hydrogen and oxygen is going to break and go onto the oxygen as a pair of electrons to give me my final answer and water as a side product coming from this H3O+ that lost their bond to oxygen or to hydrogen. How do you know if it will be a Friedel-Crafts reaction or a irreversible acyl addition reaction? Yeah, that's a good question. So Friedel-Crafts reaction, right, is a type of EAS mechanism reaction. An EAS mechanism reaction involves benzene as a nucleophile. So that's the biggest factor signal. When you see benzene, right, then it's most likely well, that's acylation. We could do acylation later, but let's say alkylation, like that. That's Friedel-Crafts alkylation when you have a benzene ring right there with this reagents for Friedel-Crafts alkylation. Friedel-Crafts alkylation will not have MGBR. They would have a haloalkane and a metal catalyst. Whereas a Grignard reagent reaction will have a carbonyl for this class, right? Reacting with R, MGBR, second step, acid workup, right? So this reaction here is Friedel-Crafts alkylation. This reaction here is organometallic, specifically Grignard reagent, right? So I've noticed that a lot of students, like, they get overwhelmed by like the many substituents, many reagents that are very similar to each other, and they like, you know, commonly mismatch them. So it's very hard to determine what reaction is what. But what I recommend is that when you guys do these reactions here, and do practice, right? Name the reaction and practice the mechanism behind it. And when you guys do the mechanism, explain to yourself like why each arrow moves the way they do, why the formal charge goes there, and stuff like that, right? Because so that's gonna help you understand the reaction better and like categorize and organize the reactions better, right? Because the RMGBR here, like I gave you guys, could have been like this. It could have been MG BR, and the R group could have been the exact same thing as the reaction here, the exact same R group, right? So a lot of students, like when they do practice problems and they like don't try to understand things, this is when they fall into the trap of mismatching the reactions, right? That's why you gotta like understand like the other stuff, like the reactant and the reagent. This is a carbonyl, this is a Grignard reagent, MGBR. And then when you have that, know the chemistry behind them, like know the properties behind them. Like we said earlier, this carbon has a partial positive charge on that carbon, whereas this Grignard reagent has a partial negative charge right there. Break it down to the fundamental concepts you learned in 1A. We have a nucleophile here, electrophile here. What would that do? Nucleophile attack electrophile, right? So understand each reagent. And we have a benzene here, and then we have this specific set of reagents here with the metal catalyst. What would that do? Chlorine attacks, and then we proceed with the EAS reaction, right? So don't get trapped by like recognizing similar reagents, because that is not gonna help you determine what reaction it is, right? You have to also analyze what reactant is given to you and what other reagent is given to you, and know the chemistry that way. Yeah. Okay, that's a mechanism for organometallic reagent. It's the exact same thing if you see Li, like lithium, it would do the exact same thing, but instead of MgBr, you just see Li. Exact same mechanism though. And all of these arrows here are irreversible. We can't go backwards. All right. Okay. Any questions on this organometallic reagent? Wait, I'll be right back. I need to do something. Okay, so let's move on to the other irreversible nucleophilic acyl addition reaction, which is the reduction of carbonyls using reducing agents of carbonyls. Reducing agents are reagents that reduces things, right? Reduces molecules, like carbonyls, for example. Reducing agents. And there's two that she introduced to you guys. LiAlH4 or NABH4. When you see this, what comes to mind? What ion comes to mind when you see a lot of hydrogens here? Right? Let's say we think of a hydrogen, but what charge would that hydrogen have? A negative charge or a positive charge when we think about these reducing agents? Negative charge, hydride ion. Yes. So that means that these hydrogen ions here, these hydride ions, are they going to act as a, oh shoot, as a nucleophile or an electrophile if we break it down even further, like with the negative charges? Nucleophile, yes, because they have that negative charge right there, right? So now, let's say we bring in a basic carbonyl like this, and we react it with first step, LiAlH4, second step, H3O+. I'm going to show you guys the tricks and tips on how to predict the product quickly without doing the mechanism to save time on the test, right? Or if you guys don't have like time to study for the mechanism, this is what I do. Find or locate the carbonyl carbon. I dot that, which is going to be this dot carbon right here. That carbon double bond oxygen right here is going to be converted into a single bond OH, alcohol, right? So that carbonyl, carbon double bond oxygen, gets converted into a carbon single bond OH. How many hydrogens did this red carbon have at the reactant molecule? So let's be careful here. 0, yes, because this carbon here has 4 bonds already, right? 0. What about this carbon? How many hydrogens does this carbon have? 1, right? Where do you guys think that 1 hydrogen came from? So you guys see H3O plus here, but it's actually not the H3O plus because that's the second step, right? So let's ignore the second step and let's look at the first step and what that first reagent would do to this carbonyl here, right? So you guys do see H3O plus, which will add like hydrogen to things, but that's the second step. We're not worried about the second step. We have this first step here, which is a reducing agent, and we said that reducing agent is a hydride ion right there. This blue hydrogen here is that blue hydrogen right there. So this is not the exact mechanism, and Lievens didn't go over the mechanism, so I wouldn't worry about this. But imagine this H minus here attacking that carbon, pushing the double bond onto the oxygen, popping that onto the oxygen right there to give us this intermediate here, O minus, and the hydrogen right there on that red carbon that it attacked, right? Where there's a new bond between that red carbon and blue hydrogen right there. And then the H3O plus comes in to protonate the O minus to give us our final neutral product. So if I highlight the H3O plus in yellow right there, right? One of the hydrogens of that H3O plus is on the oxygen, right? That's where the H3O plus hydrogen goes to, the oxygen. The blue hydrogen here that is invisible comes from the reducing agent, the hydride ion that attacks the carbonyl, like that, right? So these are two different H's here. And this is an irreversible reaction because we can't go backwards, right? We can't go make a carbon double bond oxygen here and kick out that leaving group because this hydrogen here, when it leaves with a negative charge, it's too unstable, right? hydrogen cannot handle that negative charge. It's too small and too non-electronegative. So that's why it cannot go backwards, right? It's going to go forward to that alcohol. Would we see one that involves a chromic acid? So you're thinking of a different reaction, right? You're thinking of H2CrO4 with heat, right? You're not going to see this reaction with carbonyls. You're going to see this reaction with benzenes and benzylic positions. So let's do a quick one. Let's say I give you this set of reagents here, right? What would the product look like here? Take some time, send me a screenshot on the Zoom, or let me know on what the product would look like here on chat. How does the blue hydrogen attach if it has a negative charge? Yeah, so this blue hydrogen here has a negative charge. So it has a pair of electrons that it could use to attack, right? That negative charge here is my nucleophile. This red dot carbon here is my electrophile because it's partial positively charged, right? We said earlier that it's attached to this electronegative oxygen atom, electrophile. In OChem, nucleophile always attacks electrophile, right? Negative charge always attacks positive charge. Like it breaks down to that in OChem, right? Like nucleophile attack electrophile. Resonance is a big thing as well. Steric hydrogens is another big thing. But we see this as a nucleophile. We're going to use this pair of electrons here to attack the electrophile, but we're going to break the octet rule when we do anything else. To conserve the octet rule, we have to pop one of the bonds of the double bond onto the oxygen, giving it a negative charge, right? So if I highlight this pair of electrons here in pink like that the hydrogen has, that's this pink bond right there. The two electrons of this lone pair of electrons are the two electrons here in that new bond, right? The red dot carbon is there, the hydrogen is there. That's the new one between the hydrogen and the red dot. Hydrogen attacks the red dot, right? And that's very different than the second step, right? Because this first reagent here is a hydride ion, the hydrogen with the negative charge. And think of this bottom one as a hydronium ion. Hydronium ion with a positive charge, H+, acidic. They're like enemies of each other. They're opposites of each other. Direct opposites of each other, right? One is nucleophilic, H-, reducing agent. One is acidic, electrophilic, with the full positive charge right there. One has a full negative charge, one has a full positive charge. Like that. Okay. Nice. Yes, so this reaction here, we are going to oxidize the benzylic carbon that has at least one benzylic hydrogen into a carboxylic acid. And Mark, you located that correctly. It's this methyl group, this isopropyl group. And what about this benzylic carbon here? Are there any hydrogens on this benzylic carbon? So let's locate all the benzylic carbons. This red dot is a benzylic carbon, benzylic carbon, benzylic carbon, benzylic carbon. And I'm going to draw in pink out the benzylic hydrogens. Hydrogen, 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 hydrogen. Are there any hydrogens on this carbon or no? This red dot carbon right here. So in this case, how many bonds do you see that this carbon has right now? How many clear bonds? It has one hydrogen because we see clearly it has one explicitly, 2, 3 bonds, right? But it's neutral. This carbon is neutral. And we know that carbon must have 4 bonds to be neutral. So its invisible bond is to that hydrogen right there. So it has one hydrogen to have 4 bonds to be neutral, like that, right? And because this is also a benzylic hydrogen on that benzylic carbon, that will also be converted into the carboxylic acid. Right? The tert-butyl group here has 0 hydrogens because that carbon already has 4 bonds. 1, 2, 3, 4. So that no reaction to that tert-butyl group because there's no benzylic hydrogen there. Right? So this whole group here will also be converted to a carboxylic acid. Yeah, the benzylic carbon is the very first carbon directly attached to the benzene ring. So this is the benzene carbon, right? And I'm going to highlight that in yellow. These are the benzene carbons here. The benzylic carbon is the very first atom attached to the benzene ring. So that's the benzylic carbon, benzylic position. Okay. like that, right? Yeah. So for this like benzylic oxidation reaction, carboxylic acid is added to whoever has the benzylic hydrogen at the benzylic position. So the mechanism for benzylic reactions, like, do you mean SN2, E1, E2, or the electrophilic aromatic substitution reactions like nitration, sulfonation, halogenation, fructose gas alkylation, fructose gas acylation? Right, because the benzene reactions like SN2, SN1, E1, E2, I don't think you need to know the mechanism for that. For the EAS reactions, you do need to know that. I did go over the mechanism for fructose alkylation, the hard one at the beginning, like one part of it. I can go over another scenario of it with the regular hydrogen shifts at some point. So the alkene, that would be a primary carbon, right? The alkene here is going to be considered a secondary carbon because it's attached to two other R groups, right? It's attached to this carbon and this carbon, two different carbons. So that's called a secondary carbon right there. This would be a primary carbon. This would be a tertiary carbon. This would be a tertiary carbon as well. Oh, no. The top one would be a quaternary carbon. Quaternary carbons, right? Because this carbon here has four groups attached to it, four alkyl groups attached to it. 1, 2, 3, 4. This carbon has one alkyl group. This carbon has two alkyl groups. This carbon has three alkyl groups. 1, 2, 3, like that. Right? So quaternary alkyl groups will not have a reaction. Yeah. Okay. So you can also see NABH4. It's going to do the same exact thing. Let me give you guys two practice problems for irreversible nucleophilic acyl addition before moving on. Right? Let's do it like this. Okay, I want you guys to predict the product and also draw out the mechanism just for practice. Okay, let's do these two problems here. Okay. Try this out. When you guys have it, you guys can send it to me on Zoom and then I could check your guys' work.
Wait, sorry, I just have a quick question. I just got here. Like that last problem, talk about the Friedel-Crafts alkylation with like the chromic acid. You said that it's only formed with primary, secondary, and is it tertiary too, just not quaternary? Or is it just primary and secondary? Oh, okay, thank you.
Oh shoot, sorry. Okay, so what I said was that wait. Who wait, was it Matthew?
Yeah, it was me. I was just getting some clarification.
Yeah. Wait. When you said thank you, did you hear me or like
No, but I get you're
oh.
trying to do with like just like clarifying
Oh,
with like
okay,
what
okay,
it
okay.
yeah.
Why did you tell me I was muted? What the heck? Oh my gosh, it's okay, it's okay.
Sorry about that. I thought you were just pointing it. I thought you were doing something. I thought you knew you were muting. My
Oh no, no,
fault.
no, no. I didn't know. Okay, okay. So the way that I did it before, right? Um, where I say this is quaternary,
Uh-huh.
this is secondary,
Uh-huh.
this is tertiary, and this is primary. I
Uh-huh.
ignored the bond to the benzene ring right there. Oh no, I didn't
Okay.
ignore that. I kept that in mind, right? Because
Okay.
I saw that carbon has 1, 2, 3, 4 carbons, right? But if you ignore that bond to the benzene ring, then you could call this a tertiary carbon right here,
Okay, okay. And
right?
uh-huh.
Mm-hmm.
And then you wouldn't form that the carboxylate or like the COO the COOH
Mm-hmm.
with the tertiary right there, right?
Yes, you wouldn't at the tertiary right here. So if you
Uh-huh.
do like this and you ignore that bond to the benzene ring, you would not form a COOH, carboxylic acid
Uh-huh.
here. Yes, that's a way to think about it. But in my opinion, the better way is to, look at the benzoic carbon here and see if there's
Yeah.
any hydrogens there. If there's 0 hydrogens there, then it would not be converted to a carboxylic acid as
I
well.
see. Uh-huh.
Yeah, but when you do pattern recognition like this, then you could also do that as well. Like the more practice you do, the more patterns you could make up, and then you could like follow that. But it's not always gonna work out because there's like different molecules for different exceptions.
Yeah.
Yeah, so it's best to understand like what's happening behind the scenes. Yeah. And like Mark said, if we ignored the bond to the benzene right here,
Uh-huh.
this group right here would be primary instead of secondary, right? Like Mark said earlier. Yeah, so you could do it like that, but you gotta ignore the bonds to the benzene ring all throughout, to keep it
Okay.
consistent. Yeah, that's good. I'm not sure what the name of this reaction is, but after these, could we please go over the mechanism where the linear structure will close up with the nitrogen in the product? So I think you're thinking of intramolecular reaction. Linear structure will close up with the nitrogen in the product. Close up the nitrogen in the product. Are you thinking about intramolecular imine formation? Yeah, can you send me an example of that on chat? But this reaction here is benzylic oxidation. Yes, and yeah, I could go over problem 1 on practice quiz too as well. Does anyone have answers to these practice problems here? Okay, so let's do the shortcut way, the trick way. What I like to do, I like to dot my carbonyl-carbon star my carbon directly attached to the Grignard reagent, MGBR. Yes, OH, terbutyl. Okay, so this is good. Thank you, Yana, for sending the answer, right? Because even if we make mistakes, we're gonna learn from it and we're gonna avoid it in the quiz tomorrow. So what Yana put for the first product is like this right here. He put terbutyl here, OH, right? But let's say that this is the dot carbon right here. That means that this would have been the starred carbon. And right now, it looks like the starred carbon is attached to 3 methyl groups. But this starred carbon here is not attached to 3 methyl groups. It's attached to a terbutyl group, right? So this is not the answer, right? A lot of people also would have made the same mistake as well, right? Yeah, that's right. Right. So that's why I like starring and dotting. Did you just do this like by looking at it? Did you star and dot it, or did you just like went for the product? Right, let's say this is star. That's like this is star. Oh wait, this is dot. This is star. The star here is attached to this terbutyl group like that, and you could draw it like here, down, here, or the way that I did it here. But do not draw it like this, right? Because it looks like this is one long single bond right there. Unacceptable. Yeah, you just went for it. Yeah, that's good. So that it could be tricky like that. That's why I like starring and dotting. It's a OP technique to keep track of all the groups. Oh, I see what you mean, Fernando. That is an intramolecular imine formation. Yes. Yeah. Okay. I'll go over that mechanism after. Okay. Okay, so the end of the session, I'm gonna go over this, that intramolecular immune formation, and then problem 1 on practice quiz 3. And if you have time for anything else, we'll do that too. Okay, so Yana, convert the carbonyl into alcohol. Yes, that is correct. That's the right answer. That 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3. Yeah, this carbon double bond oxygen here gets converted into a single bond oxygen alcohol right there. Nice. Okay, let's move on. Let's do reversible. Yes. Okay. So for this last problem here, if you want to do the shortcut, right? This is what we do. We locate the carbonyl carbon right there, which is this purple carbon right here, right? And then your carbon double bond oxygen, that's the carbonyl right there. You just convert it into the single bond alcohol. So that's the quick way. But if you want to understand it for mechanism, this is what you do. When you see NaBH4 right here, what ion comes to mind? Like let's say you have a lot of hydrogens. We know that there's going to be a hydrogen here, but with what charge? With a full positive charge or with a full negative charge here? What ion what do we think about when we think about reducing agents? Negative charge, right? Which makes this our nucleophile. And we know that the carbonyl carbon is electrophilic. So this is not the correct mechanism, but she didn't go over it. But this is what it would go like. This nucleophile H- here is going to attack that electrophilic carbon to conserve the octet rule. We're going to pop this double bond onto the oxygen to give us this intermediate here, right? Or this is the purple dot carbon. We pop the double bond oxygen into a single bond O-. This is the new bond between the purple dot carbon and the hydrogen that attacked that purple dot carbon, right? And that's this hydrogen right here, but I kept that as invisible, and you can keep it as invisible for the product. Now we bring in the second step, hydronium ion, H3O plus, to protonate and neutralize the O- by those arrows like that. Yeah. Yeah.
Just quick question. Would you get the same product if you use LiH4?
Yes, it will be the
Okay,
same product if you use LiLH4. That's a good question, right? LiAlH4. So in this quiz, you don't worry about the differences between NaBH4, LiAlH4. They'll give you the same thing, right? Don't worry about that. But when you learn about carboxylic acids and their derivatives, right? Not calculus derivatives, we're not going to do any math. It does matter which reducing agent you do use now, right? But for now, don't worry about that. That's a good question. What is the difference between the red and black structures? So the red structure is the product, the black structure, the intermediate, the mechanism. Like this is just showing the mechanism on how to get to this final correct product here. Right. This is the intermediate. This is like the second step, hydronium ion, to reach to this product here. Yeah. This is just the mechanism. But I don't think this is going to show up in the quiz. That mechanism is too short. How come you didn't include the extra bond to purple? Oh, okay, yeah. So yeah, someone else asked, where did this ethyl group come from? Right. That ethyl group is not there, right? That nice catch. That purple dot carbon here is attached to. Oh, I drew this entirely wrong. Like this purple dot carbon is not attached to those groups at all. So that's why I like starring and dotting my atoms, right? The correct structure here would be like this. So let's draw it in black to keep it straight. This is the purple dot carbon right here. Nice catch, guys. That is attached to that big bulky group, whatever this is, a methyl group, a single bond O-, or a single bond OH now because we protonated it, and an invisible hydrogen coming from the hydride ion, the reducing agent, where this is the final answer. That's the correct answer. Nice. I'm still confused on how to get the ethyl from methyl. Can you explain that again? Yeah, so did that make sense? Like I drew the wrong answer the first time because I was kind of rushing through it. Right, but that's why take your time. Well, there's barely any time in the quiz, but try to take your time and start out your groups and don't do that monstrous, atrocious thing that I just did on the quiz. Okay, that's good. Yeah. Good thing you guys stopped me for this problem. That's good. Okay, so for reversible nucleophilic acyl addition. Right, and that's the thing about the Lievens quiz too. Like that time pressure can make you guys forget things and mess up too. So that's a big problem. So reversible nucleophile acyl addition. So this practice in time conditions, like practice doing practicals in under time pressure. These are gonna use reversible nucleophiles. Right, and for vocab, the pKa of these reversible nucleophiles are going to be less than 25. And the common ones are going to be hydroxide ion, alkoxide ion, cyanide ion, and neutral amine, right? It could be ammonia. It could be primary amine. It could be a secondary amine, right? And then this is right here is going to form our imines or enamines. Okay, now there's 4 types of reversible nucleophilic acyl addition reactions that she went over. There's the cyanohydrin formation. There's the enamine formation. And then there's the geminodiol formation for the reversible nucleophilic acyl addition. Geminodiol or hydrate. Geminodiol, aka hydrate. Okay, so cyanohydrin, that is going to have an alcohol and a cyanyl group on the same carbon, like that. Imine, that is going to have it's like a carbonyl, right? Carbon double bond oxygen, but it's going to be a carbon double bond nitrogen now. And for that nitrogen to be neutral, it has to have 3 bonds. So it's either going to be attached to a hydrogen or some random R group to be neutral. That's the imine. The enamine is going to have some sort of amine that has 2 R groups, no hydrogens, and an alkene nearby, right? Enamine, alkene next to amine, enamine, alkene next to amine, enamine. So that's a way that you could look at that. Geminodiol or hydrate is when we have 2 alcohols, right? That's the diol part. 2 for di, O for alcohol. 2 alcohols on the same carbon. That's geminal. The geminal position on the same carbon. This is also known as a hydrate, right? And all of these right here can be formed from a carbonyl, right? All of these functional groups that I just gave out can be formed from this carbonyl here by nucleophilic acyl addition reversible. Right, it's just gonna use different reagents to do so. Okay. Now let's do cyanohydrin formation. Let's say we have this carbonyl here, and we want to get to this cyanohydrin here. OH, CN.
That's so real.
And we want to have the NaCN or KCN, they're the same thing, and HCN, right? Because whenever you guys see Na or K, always associate that with a positive charge, right? That means that whatever is attached to it is negatively charged. Our negative charge thing here is the Cn minus, like that. So to predict the product quickly, if you see this on the quiz, locate the carbonyl carbon, which is that pink dot carbon right there. And then when you see these set of reagents here, NaCN or KCN with HCN, convert the carbonyl into an alcohol and attach a CN there. You could also draw it like this as well. Right, they're the same thing. Whichever way looks nicer for you, you could draw it. They're the same thing. Now, here's the mechanism. Cn minus is my nucleophile because it has the full negative charge. This carbon-to-carbon, like we said earlier, is my electrophile because it is partial positively charged. Why do you attack the negative part instead of the positive part? For this mechanism here, so this mechanism here, the negative charge here is going to attack the positive charge here, like that. So that's the arrow, right? This negatively charged Cn minus attacks that positive charge carbon. But like we said earlier, that's going to break the octet rule. So to conserve the octet rule, pop one of the bonds onto the oxygen, onto the oxygen right there, to give us this intermediate here. O minus Cn, right? And then our acid source, proton source, HCN, is going to come in to protonate and neutralize the O minus. O minus grabs the hydrogen, bond between hydrogen and cyanide kicks off to give us our final answers there. Short mechanism. Did that answer your question? The positive charge never attacks the negative charge at all, right? In this mechanism, no positive charge attacked any negative charge. This negatively charged cyanide ion here attacked this positively charged carbonyl and then popped the double onto the oxygen to get this tetrahedral intermediate. And then we did an acid workup step to neutralize the O minus right there. Okay, so that's cyanide formation. So it's the negative part that's attaching because C has the partial positive. Yes, this carbonyl C here, because it has the partial positive, is my electrophile. This Cn minus here, because that's the full negative charge, is my nucleophile. And in OChem, nucleophile always attacks the electrophile. Negative charge always attacks positive charge in that direction, not the reverse, right? Do not draw an arrow from a positive charge to a negative charge. That is not good. Right.
I had a quick question.
Yeah.
So the sodium or the potassium or whatever it is, it just kind of disappears, right?
Yes, it disappears into ions. It's just like it's still floating around like that. But since it's inorganic, you don't have to put it in your product because it's inorganic. Right. Okay. Can you clarify the trapped cyanohydrin with second irreversible step? Yeah. So there's two ways that we could trap this cyanohydrin, right? Because all of these right here, I should be drawing reversible arrows to be more accurate, right? Or reversible. We could go back and forth. Oh shoot, this way, this way. Yeah, reversible. It could go back and forth. But let's say you want to trap the cyanohydrin, right? And you want to like make it go irreversible to some molecule that would like store the cyanide into like a locked vault somehow. There's two reactions to do so. So let me draw out a cyanohydrin here, OH, and cyanide here. There's two reagents that you're going to see with this. H2PDC and H2O and H2SO4. The first reaction, H2PDC, whenever you guys see that, think of that as a type of reducing agent. Reducing agent, right? A lot of reducing agents tend to have a lot of hydrogens to them, right? H2. We're going to reduce this nitrile here into an amine, NH2. So this is the amine right here. If I highlight this nitrile carbon here in yellow, that's that carbon right there in yellow, right? I made this mistake before. Avoid this mistake. Do not do this when you see this reaction. NH2, right? That's not it. Not the right answer because we're missing this carbon here. We're missing that yellow carbon right there, right? It doesn't disappear. It's still right there. Yeah. Right. So let's cross this out. That's not the right answer because it's missing that yellow highlighted carbon. Okay. Now H2O, H2SO4. You're gonna learn more about this in the next quiz. This is gonna do a hydrolysis reaction, which it's just going to convert the cyanide group into the carboxylic acid. She did go over that for this quiz. So just convert that nitrile group into this carboxylic acid here, where that yellow highlighted carbon is this yellow highlighted carbon right there, like that, right? So that red circle right there, cyanide converts to CNH2 or COOH, depending on what reagent you use, right? Reducing agent H2PDC or hydrolysis with water and strong acid, H2SO4. And this traps the cyanide because this is, well, the first one here is irreversible, right? Irreversible, where we stop right here. Well, actually, I wonder if there's a way to oxidize the NH2 back into the cyanide, but I haven't seen that yet. There might be a way. So I'm not going to put that just in case there's a way, right? But I haven't seen that. But this right here is definitely reversible. But what this did, right? If you think about it big picture, it converted this CN nitrile into CnH2 or COOH, which makes it like more stable molecule, you could say. Like these right here are more stable molecules, right? More stable and can be isolated. This molecule here is less stable because this carbon right here is attached to two electronegative atoms, oxygen and nitrogen, making that carbon extremely positively charged, extremely electrophilic, extremely reactive, right? So this is not as easy to isolate because it's very reactive, right? And it's very reactive because of this big positive charge on the carbon attached to a lot of electronegative atoms, right? Whereas the carbons here are only attached to one electronegative atom, making it a smaller positive charge, less reactive, more stable. Easy to isolate, easier to isolate. Easier to isolate or trap the cyanohydrin. Did you attach the H2 to the nitrogen because nitrogen is more electronegative? So the H2 here is actually gonna go to that yellow carbon right there, right? If I color code the H2 here in blue, like this, that two H's are gonna be these two H's here on the yellow carbon, right? The two H's here will come from some acid source, proton source, right, in the solution. But don't worry about the mechanism here. You don't need to worry about that, right? But the two H's here on the nitrogen are not the two H's here on the reagent, right? But it's good that you're thinking about the mechanism on how, like, where the H's come from, because that's how you should be studying for these quizzes and OChem. Like, look up behind the picture, see things. Yeah. Okay. So now let's go over. So germinodiol, I don't think that's gonna be for particular products. I'm gonna skip that. That's more for like conceptual stuff, like when you can isolate them, when you cannot isolate them. But I want to go over the imine and enamine first, and then move on to the quiz questions that you guys asked for. Okay, so imine, right here. That is, like we said, a carbon double bond nitrogen, and that nitrogen can be attached to a hydrogen or an R group. This imine here will react the carbonyl with either ammonia, NH3, or a primary amine, right? A primary amine could be anything like this, NH2, NH2, NH2. All of these here are primary amines because the nitrogen here is attached to one other carbon like that. That's why they are primary amines, right? Now, let's say we have a simple carbonyl like that, and we react it with ammonia and some sort of acid, HCl. To predict the product quickly, locate the carbonyl carbon, that's the one in red right there, and we're gonna substitute the oxygen with the nitrogen, right? There's still a double bond right there. But if I highlight this nitrogen here that replaced that oxygen in yellow, that's gonna be this nitrogen here in yellow, right? And for this imine formation, you could think about it as -2 hydrogen. Before, it had 3 hydrogens. 3 minus 2 is 1. So it's going to have 1 hydrogen there. That's the final product, right? Now, that's important because let's say you have this primary amine instead at HCl, right? Let's do the same thing. Locate the carbonyl carbon in red, like that, and we substitute the oxygen with the nitrogen like that. This nitrogen here in yellow is going to be that nitrogen there in yellow. Do the same trick when we predict the product quickly without losing the mechanism, -2 hydrogen. This nitrogen here has 2 hydrogens. 2 minus 2 is 0. So this nitrogen will no longer have any hydrogens, right? But it is still attached to this R group with 1, 2, 3, 4 carbons. So draw that out like this. 1, 2, 3, 4, like that. Whatever the R group here, the decoration is here, just copy and paste that over to the nitrogen because it follows with the nitrogen right there. Okay, so I'll go over the mechanism if I have time at the end, but I want to go over the other questions that was sent. Why is the oxygen replaced? Yeah, so that's gonna talk about the mechanism on why it's replaced. Actually, yeah, let me just do it here, the mechanism really quick. And I'm going to do it with the primary amine. So here's the mechanism. This is the carbonyl, carbon double bond oxygen. This is my primary amine right here. I have HCl. So the way that Lievens does it, this nitrogen here with a pair of electrons is my nucleophile. This carbon here, we know its partial positive charge is my electrophile. We know the direction where the arrow is going to be at. Nucleophile to electrophile, negative charge to positive charge. This amine attacks that positive charge to conserve the octet rule, pop that double bond onto the oxygen. And this is reversible nucleophilic acyl addition, so make sure to draw reversible arrows here in the mechanism. Or I think Lievens will give it to you anyway, because like she gives you boxes and then she gives you the reversible arrows. The intermediate would be like this. This is the red dot carbon right there. This is the oxygen with the negative charge. This is the neal bond between the carbon and this nitrogen here, right? But this nitrogen here is attached to two hydrogens, 1, 2, positive charge, and the R group, 1, 2, 3, 4, which is this R group right here, right? This nitrogen is positively charged because it has 4 bonds, 1, 2, 3, 4, and 0 pairs of electrons. Now, once we get this tetrahedral intermediate, we are going to do the proton transfer step. We want to neutralize the O minus and we want to neutralize the N plus. To neutralize the O minus, we got to protonate it. To neutralize the N plus, we got to deprotonate it. So we could kill 2 birds with 1 stone here. We could protonate this O minus and deprotonate that N plus at the same time. This O minus here is going to grab that hydrogen from the N, the bond between this hydrogen and N right there. Those 2 electrons are going to go to the nitrogen to give us this neutral intermediate here, neutral tetrahedral intermediate, right? Where the nitrogen is now neutral and it has 1 hydrogen. This hydrogen is now on the oxygen right there, right? Now, our end goal, right? If you get stuck in the mechanism, our end goal is to get this imine here, that carbon double bond nitrogen with its R group. Now, this nitrogen here now has a pair of electrons. This pair of electrons came from that bond right there between the nitrogen and hydrogen, right? We want to make a double bond right there between carbon and nitrogen. That's our end goal, right? But that's going to break the octet rule when we don't do anything else. That carbon's going to have 5 bonds. 1, 2, 3, 4, 5. To conserve the octet rule, we got to kick this guy out. But this guy right here is a bad leaving group, right? So before we could do this like step where we go make the carbon double bond nitrogen and kick out this leaving group, we got to convert this bad leaving group into a good leaving group, right? So right now, this is a bad leaving group. To convert this bad leaving group into a good leaving group, we bring in the acid. And the acid that they gave us is HCl. So this O minus, this oxygen here is going to attack that H, kick out the Cl, to give us this oxonium ion, OH2 plus, which is a good leaving group, right? Now, once we have the good leaving group present, this nitrogen with the pair of electrons can make that desired double bond between the carbon and nitrogen. And to conserve the octet rule, pop that guy out, kick that guy out. And we're going to get this iminium ion. The nitrogen there is still attached to a hydrogen, right? This nitrogen here is still attached to a hydrogen, which is right there, which is why it's positively charged. And because this is a mechanism problem, I'm going to draw out the side product, H2O, right? The H2O that left. The last part here is to neutralize the positive charged nitrogen with the base, Cl minus. To grab that hydrogen, bond between the hydrogen and nitrogen goes there to give us this neutral imine there, right? So that's why this nitrogen here substituted that oxygen, right? Because of this whole mechanism here. The nitrogen attacks, and then we do a proton transfer step to get to this neutral intermediate. Now, we want to get rid of this guy, and we want to keep this guy, right? But we got to convert this guy into a good leaving group first before we do that. And to convert that guy into a good leaving group and then positive charge, we protonate it with the acid we have, HCl. Then we make the double bond between carbon and nitrogen that we want and kick out the good leaving group to get this intermediate. And then we get the final neutral product by deprotonating it with the conjugate base, right? So this could be a no-card thing, but when you do practice, I would do what I just did. Talk yourself through the arrows, the charges, why it attacks that, nucleophile, electrophile, the pairs of electrons. You could draw that out as well to keep track of your formal charges. But that's the most important part, the formal charges, right? Because if you put like a negative charge on this O minus right here, you don't have to include negative charges because they're implied like that, right? As long as you put that negative charge right there. But you can if it helps you figure out what the formal charge is, like that. Okay. Any questions on this mechanism for imine formation? And that was kind of fast because I want to get through the other problems as well. Okay, so let's go over Fernando's question. If Fernando is still here, which is imine, yeah, he is still here. Formation intramolecularly, right? So he sent this problem, which is W from Lievens practice worksheet. We have this aldehyde carbonyl reacting with this and HCl catalyst. Right, it's an HCl catalyst because it gets reformed in the mechanism. We see that when the Cl minus here grabs the hydrogen in the last step, we reform HCl as the catalyst. Okay, so imine formation, we see that it is a carbonyl reacting with either ammonia or a primary amine in acid, let's say HCl for example, because that's the common one that Lievens uses, and that's going to form an imine. Right, let's analyze this problem here. We have a carbonyl, but on the arrow, this is different, right? There's no amine on the arrow, but there is an amine somewhere here in the molecule. Would this be a ammonia, primary amine, secondary amine, or tertiary amine? Which one of these amines would it be? Could you elaborate? Let's see here. Yeah. What if nitrogen only has one H? Yeah, that's a good question. We're gonna go over that, Chris. When we go over enamines, when nitrogen only has one H, that's when you form enamines. Yeah, this is a primary amine because this nitrogen here is only attached to one other carbon, and because we have a primary amine with a carbonyl, right? So let's locate all the things that we need for imine formation. All the ingredients for this reaction: carbonyl right there, primary amine right here, acid right here. These three ingredients, carbonyl, primary amine, and acid, is the recipe for forming enamines. I mean, imines with the I, not enamines, right? But this right here, notice how the nucleophile is on the same molecule as the electrophile. This is my nucleophile. This is my electrophile. When the nucleophile and electrophile are on the same molecule, right? It's a special type of reaction known as the intramolecular reaction, right? And you guys got to know intramolecular Friedel-Crafts alkylation. That I have a feeling that for some reason that's going to show up somehow. Intramolecular Friedel-Crafts alkylation, right? Intramolecular reaction. There's different types of intramolecular reactions. This is one type that we're going over right now. Intramolecular Friedel-Crafts alkylation is one. Intramolecular Williamson ether synthesis is one. But all intramolecular reactions will always form a ring. Forms a ring. Right? So that's why you saw that ring in the product right there. So when we think about this mechanistically, let's do that right here. So this is like harder to predict the product by the pattern recognition, but the tips and tricks. You actually have to like think about it mechanistically kind of. But I'm going to show you the trick. There is a trick that you can do it faster without doing the mechanism. But before that, let's do the mechanism first. This nitrogen here attacks the carbonyl. Pop the double bond onto the oxygen right there. That's going to give me this intermediate right here. Right? But we know we're going to form a ring. And the way that I'm going to number this is like this. I'm going to number my number one atom, the nucleophile atom, that nitrogen right there. And I'm going to go all the way until I hit my electrophile. I hit it at carbon number 5. So I know that I'm going to make a 5-membered ring. So let's draw that 5-membered ring out like this, where I know that nitrogen is part of the 5-membered ring, like that, right? So this is going to be atom 1, atom 2, atom 3, atom 4, atom 5. That's the 5-membered ring that we form right there. If I highlight that backbone of the ring in yellow like this, that's this backbone right here. This nitrogen, 1, 2, 3, 4, 5, like that, right? That yellow highlighted part is this yellow highlighted part. We closed the ring, right? This nitrogen closed the ring. We made a new bond between 1 and 5. Before, there was no bond between this nitrogen atom and this carbonyl carbon atom, but we made that new bond right there, right? This is the new bond right here between 1 and 5. It was not there before, but we made that happen by attacking that carbonyl with this nitrogen, right? Now, everything is copy and paste, decoration. Nitrogen is attached to 2 hydrogens, 1, 2. Carbon 2 right here is attached to an ethyl group. Carbon 2, ethyl group. Carbon 5 is attached to a hydrogen. I'm going to leave that as invisible. and it was attached to a double bond oxygen, but we popped that up to make a single bond O minus, like that, right? And let me make the ethyl group somewhere else where it's not like in the way of the hydrogen, like this. Ethyl group 1 carbon 2. Like that. Okay? And because this oxygen has 1 bond, 3 pairs of electrons, it's negatively charged. Because this nitrogen here has 4 bonds, 1, 2, 3, 4, and 0 pairs of electrons, it is positively charged, right? So now, does that make sense on like how that formal charges formed? Don't forget those formal charges on the quiz if this was a mechanism problem, right? I have a feeling that there might be an intramolecular mechanism, maybe. Or if not, predicted product for sure. Now, this is the proton transfer step. We kill 2 birds with 1 stone here. Protonate the O minus, deprotonate the N to neutralize this intermediate in 1 singular step, right? Other professors like Nasseri, Mascal, they don't like killing 2 birds in 1 stone like that. But Helix and Lievens, they're chill. They allow this fast step here. Right? Okay. So that gives us our neutral intermediate right here. Now, what do you guys think the next step is going to be? Our end goal is to form an imine, a carbon double bond nitrogen. So let's say we want to form a double bond right there. But before we can do that, what do we have to do first? Yeah, alcohol gets another proton. We got to protonate it to convert it into a good leaving group. How do you know that one of the bonds has to move to the oxygen to give it a negative charge? Yeah, so this arrow here, right, where we move one of the bonds to oxygen to give it a negative charge is required because when this nitrogen here, the nucleophile attacks the electrophile, and we make a new bond between that nucleophile and electrophile, this carbon here is going to break the octet rule if we don't do anything else. It's going to have 5 bonds. 1, 2, 3, 4, 5. That's not good. We got to conserve the octet rule by pushing that bond onto the oxygen to maintain the octet rule here, like that. Right? And how do you assume that the N in the NH2 has a positive charge? So this N here has a positive charge because before it had 1 pair of electrons. We use that 1 pair of electrons to make a bond between 1 and 5 like that. Those 2 electrons that are in that bond is that 1 pair of electrons. This nitrogen right here is positively charged now because it has 0 pairs of electrons and has 4 bonds. 1, 2, 3, 4. When we calculate formal charge, look at what the atom is on the periodic table. 5th column, it wants 5 electrons to itself. But right now it has 1, 2, 3, 4 electrons to itself. 5 minus 4, positive 1. Formal charge, positive 1 nitrogen, like that. You can do the same for O minus for practice, right? Now, for this way, like Yana said, this OH bad leaving group here is going to get protonated by HCl to convert that into a good leaving group, which is going to be this OH2 plus here. Now, once we have that good leaving group, this nitrogen with the pair of electrons right here, right? It gained a pair of electrons from like this deprotonation step, right? That bond right there. That pair of electrons can make a double bond right here and kick out that good leaving group right there, which would give us almost our final product, right? We have our carbon double bond nitrogen now, which is good. Our iminium, our imine bond, but this is not an imine yet because that nitrogen is still attached to its hydrogen with a positive charge. And we could draw water out as a side product. This is what we call an iminium ion. Right? It's not an imine yet because it has a positive charge, an ion attached to it. Where the final step is to deprotonate it with Cl minus and reform our acid catalyst HCl. Right? And give us our neutral imine here. Right? With 1 pair of electrons and HCl gets reformed. So this is a cyclic imine. It's an imine in a ring, in a cycle. Cyclic imine. So that's an intramolecular imine formation right there. Cyclic imine. Okay. Any questions on this problem here? The intramolecular imine formation? Okay. So, since it's close to 11, do you guys want to extend this session by 1 more hour, or is it getting too late? I know you guys have your quiz tomorrow at 8 a.m.
Wait, I have
Yeah.
I have a quick question.
Yeah.
You know these problems you're doing? Can you post in the Discord or something like that if that is okay?
Yes, I will post the notes here on the Discord and the recording because I'm recording this as well, this session as well,
Uh-huh.
to the Discord for you to review.
Thank you.
Yes, of course. Okay. It's bedtime. Yes, sleeping time. Well, I want to go over. I didn't go over enemy, but I didn't have time for that. I want to go over practice quiz 3 and question 1. Right, someone requested. Let me do that. Practice quiz 3, question 1. Oh, this one right here. So we went over is problem like this earlier in the session. When we see a benzene with benzylic carbons and chromic acid, H2CrO4, right? What are we looking for here? What is the thing we are looking for to look for a reaction? Right.
Isn't this like we're looking for
Uh-huh.
like the branches from like the what you call it?
Uh-huh.
The ACO? In which
Mm-hmm.
like if it's like what you said earlier, if it's like primary, secondary,
Mm-hmm.
tertiary, in
Yes.
which primary and secondary will form a carboxylic acid, but
Mm-hmm.
tertiary you won't do anything to it.
Yes, that's right. Like this one here is tertiary, this one here is primary. Another way that you can think about it, that's correct, nice, is that look for the benzylic carbons, right? Which is the carbon directly attached to the benzene ring, the first atom attached to the benzene ring, and see if there's any hydrogens attached to it, right? This one on top has 2 hydrogens. Those are the benzylic hydrogens. This one at the bottom has 0 hydrogens. There's 0 hydrogens there. The ones with at least 1 benzylic hydrogen will be converted into a carboxylic acid. So the one at the bottom, no reaction, stays the same. The one on the top converts into a carboxylic acid, like that, right? Because it has at least 1 benzylic hydrogen. Yeah, seeing which groups has one benzylic hydrogen. Nice. Okay. Yes, so the session is ending here, guys. Now I'm gonna end the session here, post these notes on the Discord, and as soon as the recording uploads, I'll send it to the Discord as well. Yeah, good luck on your quiz tomorrow, guys. Yeah.
Thank you so much.
Of course. Yeah. You got it. You guys got it. Yeah. Good night. Good night.